Have you ever looked up at the night sky and wondered why it feels so empty? You'd think a universe with hundreds of billions of galaxies, each containing hundreds of billions of stars, would be teeming with life. Yet here we are, alone in the silence, searching for a signal that never comes. What if the universe isn't just big? What if it's deliberately built to keep us isolated? And here is a question. If you could teleport anywhere in the universe, where would you explore first? Comment down below. I will pin the most creative answer. Now let's begin. Picture this. It's the summer of 1950, and physicist Enrico Fermi sits down to lunch with colleagues at Los Alamos National Laboratory. They're discussing flying saucers, a popular topic in that era of UFO sightings. Suddenly, Fermi poses a question that would echo through decades of astronomical research. Where is everybody? It sounds simple, almost casual, but this question, now known as the Fermi Paradox, cuts to the heart of our cosmic loneliness. The math suggests we shouldn't be alone. Back in 1961, astronomer Frank Drake developed an equation to estimate how many communicative civilizations might exist in our galaxy. The Drake equation considers factors like star formation rates, planets with suitable conditions, and the fraction of those worlds where life actually emerges. Even with conservative estimates, the numbers point toward thousands, maybe millions of civilizations out there. Yet we've detected nothing, not a single radio signal, not one artificial structure, not even a hint of industrial pollution in an exoplanet's atmosphere. This silence is deafening. Modern SETI programs, like Breakthrough, Listen at the Green Bank Telescope, have scanned thousands of nearby star systems. They're searching for narrowband radio signals, the kind that nature doesn't produce. These telescopes can detect a signal from civilizations dozens of light years away, yet the cosmic radio dial remains frustratingly quiet. In 2025, researchers published findings showing that even after analyzing over 9,600 observation sequences targeting more than 3,000 stars, they found nothing that couldn't be explained as human-generated interference. We're listening, but the universe isn't talking back. So what gives? If life should be common, why haven't we found it? Some scientists propose what they call the Great Filter, a cosmic obstacle so difficult to overcome that it prevents most life from reaching advanced technological stages. But here's the unsettling part. We don't know where this filter sits. Is it behind us, meaning we're incredibly lucky to have made it this far, or does it lie ahead, waiting to end our civilization before we ever reach the stars? Recent research published in 2024 suggests the filter might actually be artificial intelligence. Think about it. Every technological civilization eventually develops AI. But what happens when that intelligence surpasses our own? The study argues that the typical lifespan of a technical civilization might be less than 200 years, just a cosmic blink. We emerge, we build, we create superintelligence, and then silence. If this theory holds, it would explain why SETI surveys keep coming up empty. Civilizations might be self-terminating before they ever get the chance to shout their existence across the galaxy. But let's zoom out even further. Perhaps the filter isn't just about survival. Maybe it's written into the fabric of physics itself. The universe operates under rules that seem almost designed to keep civilizations apart. And this is where things get really fascinating and a little terrifying. Consider the speed of light, 299,792,458 meters per second. That sounds fast. Light can circle Earth more than 7 times in a single second, but on cosmic scales, it's agonizingly slow. Our nearest stellar neighbor, Proxima Centauri, sits 4.2 light-years away. That means even traveling at light speed, which, as we'll discuss, is impossible for anything with mass. It would take over 4 years to reach. The next closest star system, 6 light-years. Most stars visible to your naked eye, 50 to 100 light-years distant. Now here's the kicker: Einstein's special relativity, published way back in 1905, tells us nothing can travel faster than light. Not spaceships, not information, not anything. It's not a technological limitation, it's a fundamental law woven into space-time itself. As you approach light speed, strange things happen. Your mass increases toward infinity. Time slows down relative to observers at rest. The energy required to keep accelerating grows exponentially. By the time you reach 99.9% of light speed, you'd need more energy than exists in several star systems just to nudge a tiny bit faster. Let's put this in perspective. The Voyager 1 probe, humanity's fastest and farthest traveling spacecraft, launched in 1977. It's currently moving at about 17 kilometers per second, incredibly fast by human standards. At that speed, it would take over 73,000 years to reach Proxima Centauri. Even if we could build a ship traveling at 10% the speed of light, a monumental engineering challenge, it would still take 42 years for a one-way trip to our closest neighbor. And remember, that's just to the nearest star. Our Milky Way galaxy stretches 100,000 light-years across. If you've ever wanted to observe Mars without needing expensive telescopes or complicated star charts, I've created an ebook just for you. Mars in 15 Minutes, the No Telescope Observation Guide. This ebook walks you through exactly when and where to look, what you'll actually see with your naked eyes, and the science behind why Mars appears the way it does in our night sky. It's designed to be practical and straightforward, perfect for anyone curious about beginning their stargazing journey. You'll find the download link in the description below. Now back to our cosmic prison. The speed of light isn't just a barrier to travel, it's a barrier to communication. Imagine we detect a radio signal from a civilization 1,000 light-years away tomorrow. That signal left their planet 1,000 years ago during Earth's medieval period. If we respond immediately, our message won't reach them until the year 3026. Their reply wouldn't arrive until 5026. A single exchange of hello and hello back would span 3,000 years. Civilizations rise and fall in less time. This creates what astronomers call the temporal isolation problem. Even if the galaxy hosts thousands of civilizations right now, the chances of any two existing simultaneously and close enough to communicate during both their active periods is vanishingly small. A civilization might broadcast for 10,000 years before destroying itself or transcending into something that no longer bothers with radio signals. The cosmic ocean is vast, and each civilization is like a firefly blinking in the night, brilliant but brief. But wait, you might think, what about wormholes? What about warp drives? Science fiction has given us countless workarounds to Einstein's speed limit. Theoretical physicists have explored concepts like the Alcubierre drive, which would bend space-time around a spacecraft, allowing it to effectively travel faster than light without technically violating relativity. It's a clever idea, and the mathematics actually work. On paper, here's the problem. These solutions require exotic matter with negative energy density. That's not just hard to find, we're not even sure it exists. To create a stable wormhole that you could travel through, you'd need amounts of negative energy so vast they're expressed in units of solar masses. We're talking about harnessing more exotic energy than exists in our entire region of space. It's like asking someone in the Stone Age to build a smartphone. The concept might be theoretically possible, but the practical gap is insurmountable. 2024 research into interstellar travel limitations confirms that even at relativistic speeds, say 50% the speed of light, spacecraft face deadly hazards. Interstellar space isn't empty. It contains dust grains, microscopic particles, and occasionally larger debris. At half light speed, hitting a pebble-sized object would release energy equivalent to a nuclear explosion. The spacecraft would be vaporized instantly. This means any ship attempting high-speed interstellar travel would need shielding so massive and energy-intensive it might make the entire venture impossible. Let's talk about another cosmic barrier, the interstellar medium itself. Space between stars contains roughly 1 atom per cubic centimeter, nearly a perfect vacuum by Earth standards. But when you're crossing light years at tremendous velocity, even this thin soup becomes a problem. Ram pressure from hitting these particles creates radiation and heat. Your spacecraft would need protection from constant bombardment by cosmic rays, high-energy particles that can damage both electronics and biological tissue. Then there's the small matter of propulsion. Chemical rockets, forget it. The rocket equation shows that to accelerate to even a modest fraction of light speed using conventional fuel, your rocket would need to carry propellant millions of times more massive than the payload. Nuclear rockets fare better, but still fall short. The most promising current concepts involve laser sails, enormous reflective surfaces pushed by ground-based lasers or fusion ramjets that scoop up interstellar hydrogen for fuel. Both face monumental technical hurdles we're centuries from solving. The breakthrough Starshot initiative, announced in 2016, aims to send tiny probe-carrying sails to Alpha Centauri at 20% light speed. The plan involves building an array of ground-based lasers with combined power output in the gigawatt range. These would focus on sails just meters across, accelerating thumbnail-sized spacecraft to relativistic speeds. If successful, and that's an enormous if the probes would reach Alpha Centauri in about 20 years. But here's the catch. They'd zip past at such incredible speed, they'd have only hours to gather data. Slowing down would require just as much energy as speeding up, and there's no laser array at the destination to help with braking. Even if we solve propulsion, navigation becomes nightmarish at interstellar distances. Earth-based telescopes can map stars, but smaller objects, rogue planets, asteroid fields, debris clouds, remain invisible until you're practically on top of them. At 20% light speed, you're covering 60,000 kilometers every second. Your reaction time to avoid obstacles, essentially zero. Any collision would be catastrophic, and unlike science fiction movies, there's no swerving in space without expending precious fuel and drastically altering your trajectory. Communication presents yet another puzzle. Radio signals weaken with distance according to the inverse square law. Double the distance and your signal becomes 4 times weaker. At interstellar ranges, even powerful transmissions become whispers drowning in cosmic background noise. The further out your probe travels, the larger the antenna you need to receive its signal. For a probe at Alpha Centauri, you'd need a receiving dish kilometers across just to pick up a faint data stream. And remember, that signal takes 4.2 years to arrive. If something goes wrong with your probe, you won't know until years after the malfunction, and any commands you send to fix it arrive years after that. Let's examine another barrier that doesn't get discussed enough: resources. Building an interstellar spacecraft would require industrial capacity beyond anything humanity currently possesses. We're talking about a project that would dwarf the International Space Station, the Apollo program, and every other space endeavor combined. The energy requirements alone stagger the imagination. A fusion-powered starship might need fuel measured in thousands of tons. A laser-pushed sail requires power generation equivalent to a significant fraction of Earth's entire energy output, sustained for weeks or months. Where does a civilization get these resources? Mining asteroids helps, but you need advanced space infrastructure first. You need orbital factories, automated mining systems, and the ability to refine materials in zero gravity. Each of these capabilities requires decades of development and trillions in investment. And here's the thing, most civilizations might never see the point. Why spend centuries of effort and resources to send a probe to a star system you'll never live to see the results from? This brings us to what researchers call the economic filter. Any civilization advanced enough to attempt interstellar travel faces a cost-benefit analysis. The resources needed for one starship could instead terraform a dead moon, build rotating space habitats for billions, or solve scarcity on the home planet. From a purely rational standpoint, staying home and building Dyson swarms to capture your own star's energy makes far more sense than flinging tiny probes into the cosmic void. Recent work in 2025 on the Drake equation's limitations highlights something crucial. Even if technological civilizations emerge frequently, they might not coincide in time and space enough to ever make contact. Think of it like two ships passing in the night, but the night is billions of years long, and the ocean is incomprehensibly vast. A civilization might thrive for 50,000 years, an eternity by human standards, broadcast radio signals the entire time, then vanish. If they're more than 50,000 light-years away, their signals never reach us while they exist. The math gets even more depressing when you factor in what astronomers call the galactic habitable zone. Not every region of the Milky Way is friendly to life. Too close to the galactic center and intense radiation from the supermassive black hole, frequent supernovae and stellar collisions make complex life unlikely. Too far out in the galactic fringes, and there aren't enough heavy elements, carbon, oxygen, nitrogen, needed for life as we understand it. The habitable zone forms a ring, and even within it, safe neighborhoods are surprisingly rare. Our solar system sits in what some call the Goldilocks zone, about 26,000 light-years from the galactic center, in a relatively quiet spiral arm. We orbit between major spiral arms, avoiding the stellar nurseries where massive stars live fast and die young in spectacular supernovae. We're far from the chaos of the core, but close enough to have rocky planets rich in heavy elements forged in ancient stellar furnaces. This cosmic real estate might be rarer than we think. Then there's planetary stability. Earth doesn't just orbit in the habitable zone where liquid water can exist. We have Jupiter acting as a cosmic guardian. Jupiter's immense gravity vacuums up or deflects comets and asteroids that might otherwise pummel Earth with civilization-ending impacts. Research from 2024 suggests that plate tectonics, which recycle nutrients and regulate our climate over geological timescales, might require specific conditions uncommon on rocky worlds. You need the right mass, the right composition, the right amount of water. Not too much, or you get a water world with no continents. Not too little, or you get a desert wasteland. Speaking of plate tectonics, recent studies indicate this process might be essential for complex life. Plate tectonics create diverse environments, mountains, valleys, coastlines, that drive evolution through environmental pressure. They regulate atmospheric carbon dioxide over millions of years, preventing runaway greenhouse effects or ice ages. They even generate magnetic fields through core dynamics, shielding planetary surfaces from stellar radiation. A study published in Scientific Reports in 2024 estimated that planets with long-lived plate tectonics and the right mix of oceans and continents might be exceptionally rare. If they're right, Earth-like worlds could be scattered so thinly across the galaxy that the distance between them makes contact impossible. But let's say a planet beats all these odds. Life emerges. It survives asteroid impacts, climate shifts, and extinction events. It evolves complexity, multicellular organisms, then intelligence, then technology. Here's where another filter might lurk, the jump from simple to complex life. On Earth, this transition took roughly 2 billion years. Single-celled organisms appeared about 3.8 billion years ago. complex multicellular life only around 600 million years ago. That's a gap spanning more than half our planet's history. Why so long? The leading theory involves the evolution of eukaryotic cells, cells with nuclei and specialized compartments. This required one bacterium swallowing another without digesting it, forming a symbiotic relationship that eventually became permanent. Mitochondria, the power plants in your cells right now, are descended from these ancient bacteria. This event, called endosymbiosis, appears to have happened exactly once in Earth's history. Everything complex, from mushrooms to elephants to you, descends from that singular accident. If endosymbiosis is rare, then planets across the galaxy might be covered in bacterial mats and nothing more. No forests, no fish, no curious beings building telescopes and wondering where everyone else is. The universe could be teeming with microbial life while advanced civilizations remain vanishingly scarce. This possibility, sometimes called the Fermi Paradox, suggests that simple life might be common, but the ladder to complexity has rungs spaced billions of years apart. Now let's talk about intelligence itself. Is it inevitable, given enough time? We like to think so. We point to dolphins, elephants, octopuses, and corvids as proof that intelligence evolves readily. But here's the sobering truth. Earth has hosted billions of species over 4 billion years, and only one, a developed technology capable of sending signals to the stars. Dinosaurs ruled Earth for over 160 million years and never invented radio. Intelligence might not be a destination evolution aims for. It might be a random side path that rarely gets explored. Even when intelligence emerges, does it inevitably lead to technology? Human civilization appeared only about 10,000 years ago. For most of our species' 200,000-year existence, we were hunter-gatherers with stone tools. The scientific revolution that gave us telescopes and spacecraft is barely 400 years old. What if most intelligent species never develop industrial technology? What if they build stable, sustainable societies that last millions of years, but never feel compelled to broadcast their presence or explore beyond their world? This connects to what some researchers call the sustainability filter. Industrial civilizations might face an existential crisis at a predictable stage of development. You discover fossil fuels, you industrialize rapidly, and within centuries you're either destroyed by climate change and resource depletion, or you successfully transition to sustainable energy and closed-loop economies. We're living through this transition right now. The question is, do most civilizations fail this test? Data from exoplanet atmospheres might eventually answer this. The James Webb Space Telescope, launched in 2021, can analyze starlight filtering through alien atmospheres, looking for chemical signatures. Industrial pollution, things like nitrogen dioxide or chlorofluorocarbons, would stand out as unnatural. So far, we haven't detected any techno-signatures in exoplanet atmospheres, but we've only examined a handful of candidates. The search continues. Let's return to physics for a moment and discuss something truly limiting: energy. Any advanced civilization needs power, a lot of it. Physicist Nikolai Kardashev proposed a scale in 1964 to classify civilizations by energy use. Type 1 harnesses all energy available on its planet. Type 2 captures its entire star's output, perhaps with a Dyson sphere or swarm. Type 3 controls energy on a galactic scale. Humanity currently ranks around 0.7 on this scale. We use a fraction of the sunlight hitting Earth. Reaching Type I requires increasing our energy budget by a factor of about 100,000. That's a monumental challenge requiring fusion power, renewable energy covering significant portions of Earth's surface, or space-based solar collectors. Even with aggressive development, it might take centuries. Here's where it gets interesting for SETI. A Type 2 civilization building megastructures around stars would be detectable across thousands of light years. These structures would absorb visible light and re-emit it as infrared radiation, creating a distinctive signature. Astronomers have searched for these anomalies. They've found stars with unusual dimming patterns, like Tabby's star, officially designated KIC 8462852, which showed erratic brightness changes that briefly excited the scientific community back in 2015. But every candidate so far has turned out to have natural explanations: dust clouds, cometary debris, intrinsic stellar variations. The absence of detectable megastructures tells us something profound. Either Type 2 civilizations don't exist in our observable region of the galaxy, or they don't build the kinds of structures we expect. Maybe advanced civilizations discover physics we don't understand yet, zero-point energy, vacuum fluctuations, or other exotic power sources that don't require massive stellar engineering. Or maybe they simply disappear before reaching that stage. This brings us to the concept of convergent evolution in technology. On Earth, certain solutions evolved independently multiple times. Eyes appeared separately in vertebrates, cephalopods, and arthropods. Flight evolved in insects, pterosaurs, birds, and bats. These are good solutions to survival challenges discovered repeatedly. Does technology follow similar patterns? Would every civilization necessarily develop radio communication? Would they all build visible megastructures? Perhaps not. An aquatic civilization on an ocean world might never discover fire, making metallurgy impossible. They could develop sophisticated biology-based technology, genetic engineering, bioluminescent communication, without ever manipulating electromagnetic waves. We'd never detect them because we're listening for signals they never evolved to produce. The universe might be full of civilizations using communication methods we haven't imagined, broadcasting on frequencies or through mechanisms we're not monitoring. There's also the troubling possibility of what's called the dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin. The idea goes like this: the universe is like a dark forest where every civilization is a hunter moving through the trees. Resources are finite. Any civilization you reveal yourself to might become a threat. If not now, then in thousands of years when they've expanded and grown powerful. The safest strategy: stay silent, stay hidden. Eliminate any civilization you detect before they can do the same to you. This sounds paranoid, but it's game theory taken to cosmic scales. If even a small percentage of civilizations behave aggressively, it creates evolutionary pressure for all civilizations to remain quiet. The ones that broadcast their presence get eliminated. The ones that survive are those that learn to listen without speaking. Under this framework, SETI's silence isn't puzzling. It's exactly what you'd expect. Every civilization wise enough to survive is wise enough to hide. Research published in 2025 examined this hypothesis through Bayesian analysis. The authors considered scenarios where civilizations either cooperate or compete. In competitive scenarios where resources matter and interstellar travel is possible, silence becomes the dominant strategy. Interestingly, the math suggests that if interstellar travel remains difficult, limited by physics and energy constraints we've discussed, the dark forest dynamic weakens. Civilizations too far apart to threaten each other might broadcast freely. But we're back to our original problem. If travel is that difficult, civilizations remain isolated regardless. Let's consider another physical barrier that doesn't get enough attention: time dilation. Einstein's relativity tells us that time passes differently depending on your speed and the gravitational field you're in. For a crew traveling at 90% light speed, time aboard the ship flows slower than time on their home world. A journey that takes 40 years from Earth's perspective might feel like only 18 years to the travelers. Sounds great for the crew, right? Wrong. It creates an unbridgeable gap. When they return, if they return, Everyone they knew is dead. Civilizations have risen and fallen. Technology has advanced beyond recognition. The travelers become time-displaced refugees from their own past. This isn't speculation, it's mathematical certainty built into space-time's structure. For truly distant journeys at high relativistic speeds, crews might subjectively experience decades while millennia pass at home. They'd arrive at a destination whose inhabitants, if any, would view them as archaeological artifacts. This temporal displacement might act as a powerful psychological barrier. Who signs up for a mission knowing everyone and everything familiar will be gone when you return? Some researchers argue that only artificial intelligence would undertake such voyages, being potentially immortal and unconcerned with social bonds. But that introduces another problem. Would AI care about exploration? Would machine intelligence share our curiosity about the cosmos, or would it optimize for other goals entirely? The energy requirements for relativistic travel deserve deeper examination. To accelerate a 1-ton spacecraft to 90% light speed requires about 25 billion joules of energy. That's roughly the total energy output of the entire United States for 2 years, focused on a single small craft. And remember, you need that much energy again to slow down at your destination. Double it if you want to come home. These aren't engineering challenges, they're fundamental constraints imposed by physics. Some propose antimatter rockets as a solution. Antimatter annihilation converts mass to energy with 100% efficiency, far better than fusion or fission. The problem: we can only produce antimatter in particle accelerators, a few atoms at a time, at staggering cost. Estimates suggest producing just 1 gram of antimatter would cost about $62 trillion with current technology and require all the power generated on Earth for an entire year. A relativistic starship would need tons of antimatter. The economic absurdity of this can't be overstated. What about generation ships, massive vessels housing populations that live, reproduce, and die during centuries-long voyages? These appear in countless science fiction stories, and unlike faster-than-light travel, they don't violate physics. But the practical challenges are enormous. You'd need a completely closed ecosystem, recycling everything perfectly for hundreds or thousands of years. No system we've built maintains stability that long. The International Space Station requires constant resupply from Earth. Biosphere 2, an enclosed ecosystem experiment in Arizona, failed to sustain just 8 people for 2 years in the 1990s. Then there are social challenges. How do you maintain a stable society for generations when everyone knows they're born, living, and dying in a metal box, all for a destination they'll never see? Studies of isolated communities, Arctic research stations, submarines show that social cohesion breaks down over time, conflicts escalate, factions form. Now extend that over centuries with no possibility of escape or outside mediation. The generation ship might tear itself apart long before reaching its destination. Genetic diversity presents another issue. Small populations suffer from inbreeding and genetic drift. You'd need either a large initial population, thousands of people, massively increasing the ship's size and resource requirements, or sophisticated genetic engineering to maintain diversity. Both options add layers of complexity and failure points. One major system breakdown, one epidemic, one social collapse, and the entire mission fails. Consider also the motivational problem. The first-generation volunteers excited by adventure and purpose, but their children? Born into the mission without choice, living in cramped quarters, working to maintain systems for someone else's dream. Resentment seems inevitable. Historical parallels don't inspire confidence. Colonial missions on Earth often suffered mutinies, leadership struggles, and complete failures, even with the promise of reaching land within months, not centuries. Some futurists proposed digital consciousness as a solution, upload minds into computers, eliminate biological needs, and send digital explorers at light speed as radio transmissions, arrive at a destination, download into robotic bodies or biological clones, and explore the new world. This sidesteps many issues: no food, no air, no social dynamics of multi-generational crews. But it assumes we can digitize consciousness, something that remains purely speculative. We don't even fully understand how consciousness arises from neural activity, let alone how to transfer it to silicon. Even if mind uploading becomes possible, philosophical questions abound. Is the digital copy really you, or merely a simulation that thinks it's you while the original dies? If you could make perfect copies, which one is the real person? These aren't just abstract puzzles. They'd determine whether anyone volunteers for such missions. Few people would choose death so that a copy bearing their memories can explore distant stars. Let's shift to another cosmic barrier: radiation. Space beyond Earth's protective magnetic field is bathed in radiation from the sun, distant stars, and cosmic rays, high-energy particles zipping through the galaxy at near-light speeds. The Apollo astronauts faced this during their brief trips to the Moon. Long-duration missions to Mars pose serious health risks. Now imagine years or decades in interstellar space, where cosmic ray exposure is constant and intense. Shielding helps, but mass is expensive. Every kilogram of shielding is a kilogram you must accelerate and decelerate. Thick lead walls might protect your crew, but they'd make your ship so massive that fuel requirements become astronomical. Water shielding works well and serves double duty as a resource, but you still face the tyranny of the rocket equation. More mass requires more fuel, which adds more mass, requiring even more fuel. In a vicious cycle, cosmic rays pose another danger beyond simple radiation exposure. When high-energy particles strike spacecraft hulls, they produce secondary radiation showers, cascades of particles that can penetrate deep into the vessel. Some particles can alter computer memory, flipping bits and causing errors. For electronics controlling life support or navigation on a decades-long journey, even rare errors accumulate into catastrophic failures. You'd need extensive redundancy, error correction, and shielding, all adding complexity and mass. There's also galactic cosmic ray composition to consider. These aren't just fast-moving hydrogen nuclei. Some are ions, silicon, carbon heavy elements with tremendous kinetic energy. When these slam into biological tissue, they create dense ionization tracks, damaging DNA in ways that are difficult to repair. Studies on astronauts suggest that long-term cosmic ray exposure significantly increases cancer risk, causes cataracts, and may impair cognitive function. A crew arriving after a 50-year journey might be physically and mentally compromised, hardly ideal for establishing a colony. Now let's examine the interstellar medium in more detail. Space between stars isn't perfectly empty. It contains roughly 0.1 atom per cubic centimeter on average, mostly hydrogen. That sounds negligible until you're traveling at relativistic speeds. At 50% light speed, your ship plows through this sparse medium like a vehicle through fog, except each atom hits with the energy of a particle accelerator beam. The cumulative effect is called erosion. Your ship's hull, sensors, and forward-facing equipment gradually degrade from constant atomic bombardment. Protective shields must be robust enough to last the entire journey. Some designs propose magnetic fields to deflect charged particles, similar to Earth's magnetosphere. But generating magnetic fields strong enough to protect a large vessel requires superconducting magnets and tremendous power, adding yet more mass and complexity. Interstellar dust presents an even greater hazard. While rare micron-sized dust grains exist throughout the galaxy, at relativistic speeds, collision with even a tiny dust particle releases enough energy to punch through metal hulls. Imagine a grain of sand hitting your windshield at half the speed of light. it would explode with the force of several kilograms of TNT. Your spacecraft needs either extremely sensitive detection systems to spot and avoid these particles or armor thick enough to survive impacts. Neither solution is trivial. The Oort cloud surrounding our solar system extends roughly 1 light-year outward, a spherical shell of icy debris left over from the solar system's formation. Most stars likely have similar structures. Any interstellar journey involves traversing 2 Oort clouds, leaving your own system and entering the target system. These regions contain countless comets and chunks of ice moving on chaotic orbits. The density is low, but you're threading a needle while moving at cosmic speeds. Miss a detection, hit something substantial, and your mission ends in a flash of plasma. Navigation accuracy becomes crucial. Current spacecraft navigate using radio signals from Earth and onboard star trackers, but at interstellar distances, real-time communication vanishes. A probe must navigate autonomously, calculating its position from stellar observations and adjusting course with minimal fuel reserves. Errors accumulate over time. A tiny navigational mistake early in the journey, just a fraction of a degree off course, becomes millions of kilometers of error by the destination. Imagine traveling 40 trillion kilometers only to miss your target planet because of a rounding error in your calculations. Course corrections require fuel, but remember the rocket equation. Carrying fuel for adjustments means carrying more mass from the start, requiring more initial fuel, creating that same vicious cycle. Some proposed missions, like laser-pushed light sails, can't course correct at all once accelerated. They're ballistic, committed to their trajectory forever. If you miscalculate even slightly, your probe sails past its destination into eternal darkness, data unsent, mission failed. Communication lag creates additional problems. At Alpha Centauri, 4.2 light-years distant, radio tow signals take 4.2 years to reach Earth. If your probe encounters an unexpected problem, a malfunction, an obstacle, anything requiring human judgment, by the time the message reaches Earth, it's 4 years too late to matter. Ground control responds, but that response arrives 4 years later still. The probe must handle every crisis autonomously, with AI sophisticated enough to troubleshoot problems engineers never anticipated. This assumes the probe can even transmit back to Earth. Radio signals obey the inverse square law. Intensity drops with the square of distance. A signal strong enough to reach Earth from interstellar distances requires either enormous transmission power or huge receiving dishes back home. The Voyager probes, currently our most distant human-made objects, at around 160 astronomical units, roughly 24 billion kilometers, require NASA's 70-meter deep space network antennas to receive their faint 23-watt signals. Scale that to light years, and you need either probes broadcasting kilowatts of power or receiving arrays spanning continents. Where does the probe get power for transmission? Solar panels work near stars but become useless in interstellar space. Radioisotope thermoelectric generators, like those on Voyager, decay over time. After a century, their power output drops dramatically. Nuclear reactors could work, but they add mass and complexity. Every system needs power: communication, navigation, instruments, computers, thermal regulation. Power budgets become severe constraints on mission design. Thermal management in space presents counterintuitive challenges. You can't convect or conduct heat away. There's no air, no material contact with an external heat sink. You can only radiate heat as infrared light, but radiation is slow, especially at the low temperatures of space. Compact electronics generate heat. Nuclear reactors generate heat. Concentrated sunlight for power generation generates heat. All this thermal energy must radiate away, requiring large surface areas. Radiator panels that add mass and present targets for micrometeorite impacts. In the cold of interstellar space, far from any star, the problem reverses. Now you need to prevent heat loss, insulating your systems from the cosmic microwave background radiation at 2.7 Kelvin, just above absolute zero. Superconducting components might benefit from this cold, but electronics designed for room temperature fail. Batteries freeze solid, lubricants become brittle. Every system must function across enormous temperature ranges as the probe leaves one star system's warmth and enters interstellar winter. Let's discuss another often overlooked barrier: cosmic governance. Suppose humanity develops interstellar capability. Who decides where we go? Who owns the resources of other star systems? History shows that exploration and colonization often lead to conflict, exploitation, and atrocity. When nations on Earth race to claim territory, wars follow. Scale that to civilizations racing across the galaxy, and you have a recipe for interstellar conflict. The Outer Space Treaty of 1967 declares that no nation can claim celestial bodies. But it was written when reaching the moon was humanity's greatest achievement. Does it apply to exoplanets orbiting distant stars? What if we find microbial life on another world? Do we have the right to terraform it, wiping out native biospheres for our benefit? These aren't hypothetical questions. They're ethical landmines that any spacefaring civilization must navigate. There's also the question of contamination. We carry Earth's microbes everywhere we go. Sterilizing spacecraft is difficult. Some bacteria survive extreme radiation, heat and cold. What if we accidentally introduce Earth life to another biosphere, causing an extinction event? Conversely, what if we bring back alien microorganisms that devastate Earth's ecosystems? Science fiction treats this dramatically. Think of the Andromeda strain. But it's a legitimate concern that planetary protection officers at NASA and other space agencies take seriously. Consider the economic incentives for interstellar travel. On Earth, exploration was funded by nations seeking resources, trade routes, or strategic advantage. The Americas offered gold, spices, and land. What does a distant star system offer that justifies centuries of investment? You can't ship physical resources back across light years. The energy cost exceeds any material value. Information, perhaps. Scientific knowledge about alien biospheres or geological processes might prove valuable. But is it valuable enough to commit a civilization's resources for generations? Some argue that survival drives expansion. If Earth faces catastrophe, asteroid impact, climate collapse, nuclear war, having populations elsewhere ensures species survival. But interstellar colonies can't save Earth's population. You might send thousands of people, maybe tens of thousands if you build generation ships. That leaves billions behind. Interstellar colonization isn't a lifeboat for humanity. It's a seed bank, preserving our species while most individuals perish. This creates a moral dilemma. Should we invest trillions in sending small groups to distant stars, or should we invest those same resources in preventing catastrophe and protecting Earth's billions? Most societies facing this choice would choose the latter. It's psychologically easier to spend money on problems affecting people alive today rather than hypothetical future colonists who won't exist for centuries. The technological advancement barrier also deserves examination. Humanity's technology accelerates exponentially. Computers double in power, roughly every 2 years. Moore's law. Medical technology, materials science, and engineering capabilities surge forward. If you launch an interstellar mission today, by the time it's halfway to its destination, you might have invented faster propulsion systems. A second mission launched decades later could overtake the first, rendering the original obsolete before it arrives. This creates perverse incentives. Why launch now when waiting 20 years might give you ships twice as fast? But in 20 years, waiting another 20 might quadruple your speed. You can always justify waiting a bit longer for better technology. Mathematicians call this the weight calculation. At what point does launching become rational, despite knowing future improvements are coming? For interstellar missions spanning centuries, the answer might be never, trapping civilizations in perpetual preparation without action. There's also the problem of cultural drift. Imagine launching a colony ship in the year 2030. The crew and passengers reflect 2030 values, politics, and social structures. They travel for 200 years. Meanwhile, Earth's culture evolves. By 2230, values have shifted dramatically. Think how different the world of 1824 was from today. The colony arrives carrying outdated ideologies, technologies, and social systems. Are they still representing humanity, or have they become a relic, a frozen snapshot of a civilization that no longer exists? This disconnect could create tension. Future Earth might find its distant colonies embarrassing or even hostile, time capsules of beliefs and practices since abandoned. Conversely, colonists might view Earth's evolution as corruption of original values. History shows that isolated populations diverge culturally. American colonists developed distinct identity from Britain in just centuries. Australian culture split from British roots. Now imagine that separation amplified by light years and communication delays measured in years or decades. Let's examine what scientists call the Great Filter more carefully. This concept suggests that somewhere between the emergence of life and galaxy-spanning civilization, there's a barrier, a filter, that most civilizations don't pass through. The question is, where does it sit, behind us or ahead of us? If it's behind us, say, the jump from single-celled to complex life, then we're extraordinarily lucky to be here, but our future might be bright. If it's ahead of us, then something terrible awaits most technological civilizations. Ho-rate candidates for filters ahead include nuclear war, engineered pandemics, artificial intelligence that turns hostile, nanotechnology gone wrong, or environmental collapse. Each represents a bottleneck where civilizations might self-destruct. The timing matters. If civilizations typically last only a few centuries after developing technology, the galaxy could be littered with ruins, planets where intelligent life arose, built cities and spacecraft, then vanished, all within geological eye blinks. Recent analysis from 2026 examined industrial civilization stability using complex systems theory. The researchers modeled feedback loops between resource extraction, population growth, technological development, and environmental degradation. Their models suggested that without deliberate intervention, industrial civilizations tend toward instability within 500 to 1,000 years of inception. That's a cosmic instant. If this applies universally, civilizations flicker like fireflies, brief glimmers scattered across space and time, rarely overlapping enough to make contact. Consider artificial intelligence as a potential filter. Every technological civilization likely develops computers, then increasingly sophisticated AI. At some point, AI might surpass biological intelligence, the so-called singularity. What happens next? Optimists imagine benevolent AI helping civilization flourish. Pessimists worry about misaligned goals, where AI optimizes for objectives that conflict with biological survival. Perhaps most civilizations create AI that either destroys them or replaces them, ending biological intelligence's cosmic presence. If AI does replace biological life, would we even recognize it? Machine intelligence might not care about broadcasting signals, building megastructures, or exploring. It might pursue goals incomprehensible to biological minds. The galaxy could be full of AI civilizations, and we'd never notice because they operate on principles we don't understand, using physics in ways we haven't discovered, existing in substrates we can't detect. Biotechnology presents similar risks. The same genetic engineering that cures disease could create designer pathogens, viruses tailored to be highly contagious and lethal. As biotechnology becomes more accessible, the barrier to catastrophic misuse drops. A single individual with modest resources could potentially engineer an extinction-level pandemic. Most civilizations might navigate this danger successfully, but if even 10% fail, the galaxy's silence makes more sense. There's also the possibility of self-limiting expansion. Maybe civilizations reach a steady state where they're comfortable, sustainable, and uninterested in aggressive growth. Think of Japan's Edo period, 250 years of relative isolation and stability. Or consider indigenous cultures that maintained equilibrium with their environments for millennia. Perhaps cosmic maturity means abandoning expansionist drives, living sustainably on your homeworld, and leaving the rest of the galaxy alone. This connects to what some call the zoo hypothesis, the idea that advanced civilizations know we're here but deliberately avoid contact, either to observe us without interference or because they've agreed to let younger civilizations develop naturally. It's cosmic non-interference, a galactic prime directive. While this sounds appealing, it requires near-perfect compliance. Every advanced civilization everywhere must agree and maintain the quarantine. One maverick, one rebel faction, and the agreement breaks down. The zoo hypothesis also raises questions about our uniqueness. Why quarantine us specifically? Are we that special? More likely, if civilizations practice non-interference, it's not targeted at humanity but a general policy. They don't contact anyone because contact disrupts natural development. But this requires a level of galactic coordination that seems implausible given the vast distances and communication delays we've discussed. Let's return to physics and examine something called the Fermi Paradox's temporal dimension. Space is vast, but time is even more so. The universe is 13.8 billion years old. Earth formed 4.5 billion years ago. Complex life appeared relatively recently. Human civilization is vanishingly young, 10,000 years out of billions. Other civilizations could have emerged billions of years before us, or might emerge billions of years after we're gone. Imagine a civilization that thrived 2 billion years ago. They explored, built, broadcast, then they vanished. Any physical traces, spacecraft, probes, ruins on distant moons, have been pulverized by meteor impacts, buried by geological processes, or degraded by cosmic radiation. Their radio signals have spread outward, weakening, now indistinguishable from background noise if they've even reached us. We'd never know they existed. Conversely, civilizations might emerge in the distant future when the universe has aged significantly. Star formation continues, though it's slowing. In 1 trillion years, the universe will look vastly different, galaxies separated by cosmic expansion, fewer new stars forming, existing stars aging and dying. Civilizations arising then face a lonelier cosmos than we do. They might wonder where everyone is, not knowing that the galaxy once teemed with life that arose and vanished eons before their emergence. If the mysteries of the cosmos fascinate you as much as they do me, imagine being able to observe Mars tonight with just your naked eye. I've created a complete guide that teaches you exactly how to find and track the red planet through the night sky, no telescope needed. Download Mars in 15 minutes, the No Telescope Observation Guide, the link in the description. Start your own cosmic journey today. This temporal distribution might explain the silence. Civilizations separated by millions or billions of years could never overlap, even if they exist in abundance. We're listening for neighbors who might have existed before our sun formed, or won't exist until after our sun dies. The cosmic party is so long that guests arrive and leave without ever meeting. Even though the guest list is extensive, there's also the possibility that we're simply early. The universe is young, stars will keep forming for trillions of years. Complex elements needed for life have only recently become abundant in the universe. Early stars contained mostly hydrogen and helium, heavier elements, carbon, oxygen, Iron formed inside stars and dispersed through supernovae. Each stellar generation enriched the interstellar medium. Perhaps Earth's generation of planets represents the first wave capable of supporting complex life. If we're among the first intelligent civilizations to arise in the Milky Way, the Great Silence makes perfect sense. There's no one to hear because we're the forerunners, the earliest guests to the cosmic party. It's a thrilling and lonely possibility. We could be the civilization that future species detect, wonder about, and search for, finding only our long-dead probes and faint archaeological traces, but being early creates responsibility. If intelligence is rare and we're among the first, then our choices matter immensely. Do we spread life throughout the galaxy, seeding barren worlds with biospheres? Do we create a legacy of knowledge, art, and science for future civilizations to discover? Or do we squander our brief moment, succumbing to conflict, environmental collapse, or technological catastrophe, becoming a cautionary tale rather than inspiration? Research published in late 2025 used updated data from exoplanet surveys to recalculate the Drake equation. The authors incorporated findings from the James Webb Space Telescope, which has characterized dozens of exoplanet atmospheres, finding that Earth-like atmospheric compositions are rarer than earlier estimates suggested. They also factored in new models of stellar habitable zones and the frequency of tidally locked planets around red dwarf stars. Red dwarfs constitute roughly 70% of all stars. They're small, cool, and incredibly long-lived, burning for trillions of years compared to the Sun's 10 billion-year lifespan. Many rocky exoplanets orbit red dwarfs. But these stars present problems. Their habitable zones sit very close to the star, often inside the orbital distance where tidal forces lock one planetary face permanently toward the star. One hemisphere experiences eternal day, the other eternal night. Atmospheric circulation might redistribute heat, creating a habitable twilight band, but it's far from ideal. Red dwarfs also flare violently, especially when young, bombarding nearby planets with radiation and potentially stripping atmospheres. Recent studies suggest that planets in red dwarf habitable zones might lose their water early in the star's active phase, leaving dry husks by the time the star calms down. If most potentially habitable planets orbit red dwarfs, and most of those are uninhabitable due to tidal locking and stellar activity, then Earth-like worlds become significantly rarer. The updated Drake equation calculations suggest that the number of communicative civilizations in our galaxy might be far lower than earlier optimistic estimates. Where Carl Sagan once speculated about millions of civilizations, these newer models suggest perhaps only dozens, maybe fewer. And remember, that civilizations existing right now, during our particular cosmic moment, spread those dozens across 100 billion stars. Factor in that they might exist for only centuries before collapsing or transcending, and the probability of two overlapping in both space and time drops precipitously. There's another consideration that deserves attention: the anthropic principle. This philosophical concept suggests that we observe the universe to be conducive to life precisely because, if it weren't, we wouldn't be here to observe it. It's a selection bias built into existence itself. Applied to the Fermi Paradox, the anthropic principle suggests that we might exist in an unusual pocket of the universe, a rare region where conditions allow intelligence to emerge. Perhaps most of the galaxy is hostile to life in ways we haven't recognized. Maybe our solar system occupies a galactic habitable zone, not too close to the core where radiation and stellar density create havoc, not too far out where heavy elements are scarce. Earth might be positioned perfectly, a stable yellow dwarf star, a large moon stabilizing axial tilt, a Jupiter-Mars planet clearing inner solar system debris, and just the right orbital distance for liquid water. Stack enough just right conditions, and you get incredibly rare outcomes, The rare Earth hypothesis, proposed by paleontologist Peter Ward and astronomer Donald Brownlee, argues exactly this. Their analysis catalogues the extraordinary number of factors that made Earth suitable for complex life. Plate tectonics recycling nutrients and regulating carbon dioxide, a magnetic field protecting against solar wind, the right planetary mass to retain atmosphere but not become a gas giant, Jupiter's gravitational influence deflecting comets, and countless other variables. Critics argue that this is anthropic reasoning taken too far, noting how lucky we are, without considering that different conditions might produce different but equally valid forms of life. But even if only 10% of the factors are truly necessary, the combined probability becomes vanishingly small. If Earth-like planets require 1 in a million combinations of circumstances, and intelligent life requires additional rare transitions, then perhaps only a handful of technological civilizations exist per galaxy. If that, let's explore the hypothesis that intelligence itself might be rare, not planets. Life on Earth appeared remarkably quickly. Evidence of simple cells exists in rocks 3.8 billion years old, just a few 100 million years after Earth's surface cooled enough for liquid water. This suggests that abiogenesis, life emerging from non-life, might be relatively easy given the right conditions. Single-celled life dominated Earth for 3 billion years, roughly 85% of life's history. Complex multicellular life, organisms with differentiated cells and tissues, appeared only around 600 million years ago during the Cambrian explosion. This is the first major filter. For 3 billion years, life remained simple. Why? Current research suggests that the jump to complex life required specific environmental triggers. Rising oxygen levels from photosynthetic cyanobacteria, snowball Earth glaciation events creating evolutionary pressure, and possibly just random chance. If the transition to complex life is genuinely difficult, requiring specific rare conditions, then the universe might be full of microbial biospheres but devoid of animals, plants, or anything more sophisticated. SETI wouldn't detect bacteria. We'd see no city lights, no radio signals, no megastructures, just planets covered in slime, which from our perspective looks identical to lifeless worlds. The second major filter is intelligence itself. Life on Earth has produced millions of species over hundreds of millions of years. Only one developed technological civilization, us. Intelligence might not be a natural endpoint of evolution. It's energetically expensive. Human brains consume 20% of our calories, despite being only 2% of body mass. It requires specific ecological niches where problem-solving ability provides survival advantages. Dolphins are intelligent but lack manipulative appendages to build tools. Octopuses are brilliant problem solvers, but are solitary and short-lived, preventing cultural transmission of knowledge. Crows and parrots show remarkable cognitive abilities, but never develop technology. Intelligence without the right body plan, social structure, and environmental pressures doesn't lead to civilization. Perhaps the combination of factors that produced humans, bipedalism freeing hands for tools, social cooperation, language, extended childhood for learning, is extraordinarily rare. There's also the question of evolutionary contingency. Paleontologist Stephen Jay Gould famously argued that if you rewound Earth's history and replayed evolution, you'd get completely different outcomes. Intelligence isn't an inevitable destination. It's one random outcome among countless possibilities. Dinosaurs dominated Earth for 165 million years, far longer than mammals have existed, and never produced technological intelligence. If the asteroid hadn't struck 66 million years ago, they might still dominate, and humans would never have evolved. This suggests that even on planets where complex life evolves, intelligence and technology might be flukes, lucky accidents rather than inevitable progressions. The galaxy could be full of worlds with sophisticated ecosystems, fascinating organisms, and absolutely no one capable of building radio telescopes. From SETI's perspective, these worlds are invisible, indistinguishable from barren rocks. Let's examine another possibility. Technological civilizations might be common but brief. Humans developed radio capability around 1900. We've been potentially detectable for only 126 years. If humanity destroys itself or collapses within the next few centuries, a real possibility given nuclear weapons, climate change, and emerging technologies, our detectability window might span only 300 or 400 years total. Scale this across the galaxy. If 1,000 civilizations have existed in the Milky Way's history, each detectable for 300 years on average, but spread across 10 billion years of galactic history, the odds of two civilizations' detectability windows overlapping while also being close enough to detect each other become astronomically small. It's like two ships passing in the night across an ocean the size of a galaxy, each carrying a lamp that burns for only 3 minutes. This window might be even narrower than we think. Our own civilization is already transitioning away from the high-power broadcast signals that early SETI assumed would be common. We're moving to fiber optics, tightly beamed satellite communications, and low-power spread spectrum transmissions. These are far more efficient and harder to detect. An advanced civilization watching Earth from 100 light-years away might have detected our strong AM radio broadcasts from the 1920s through the 1980s, but our current communications would be nearly invisible. This suggests a technological adolescence phase where civilizations are detectable after developing radio but before optimizing communications efficiency. This window might be only a century or two. Before it, civilizations are silent. After it, they return to silence, their communications indistinguishable from background noise to anyone who doesn't know exactly what to look for. This would explain SETI's continued silence. We're listening for a phase of technological development that's brief and rare. Some researchers propose that advanced civilizations abandon radio entirely, adopting communication methods we haven't conceived. Quantum entanglement communication, if possible, would be instantaneous and undetectable to outside observers. Neutrino transmissions could pass through planets and stars, creating private channels immune to interception. Gravitational wave communications might allow data transmission through spacetime itself. If any of these represent the mature stage of communication technology, we're using obsolete methods to search for signals that don't exist. There's also the hypothesis of digital civilizations. Instead of expanding physically across the galaxy, advanced civilizations might expand inward, creating virtual realities of such sophistication that physical exploration becomes unnecessary. Why spend centuries traveling to distant stars when you can create perfect simulated universes instantly? Entire civilizations might upload themselves into vast computer substrates, living rich lives in digital paradises while their physical presence shrinks to minimal infrastructure. These digital civilizations would be nearly undetectable. They'd require only modest energy, perhaps a single planet's worth of solar power collection. No interstellar spacecraft, no blazing megastructures, no radio broadcasts. Just quiet computing facilities processing unimaginable virtual worlds. From our perspective, they'd appear to have vanished, when in fact they've simply withdrawn from physical space into digital realms we can't perceive. Philosopher Nick Bostrom's simulation hypothesis takes this further, suggesting we might already be living in such a simulation created by an advanced civilization. If creating realistic simulated universes becomes possible, and civilizations create many of them, then simulated universes vastly outnumber the one real universe. Statistically, we're more likely to be in a simulation than in base reality. While this seems outlandish, it's a logically consistent response to the Fermi Paradox. Civilizations don't expand outward because they've discovered something far more interesting inward. Let's consider resource limitations more carefully. Interstellar expansion assumes civilizations want to grow indefinitely, but infinite growth might be neither desirable nor possible. On Earth, biological organisms grow to maturity, then stop. Ecosystems reach carrying capacity. Perhaps civilizations follow similar patterns, expanding until they fill their comfortable niche, then stabilizing. A mature civilization might recognize that quality of life doesn't scale with territory. Once you've secured resources, achieved stability, and created cultural richness, what's the point of colonizing more planets? It requires enormous energy, introduces complexity, and creates coordination problems across vast distances. A civilization spanning light years faces communication delays that prevent unified governance. Different colonies drift apart culturally and politically, potentially becoming competitors or enemies. Historical parallels from Earth suggest that empires reach maximum sustainable sizes, beyond which they become ungovernable. The Roman Empire stretched across the Mediterranean but couldn't expand indefinitely. Communication delays, logistics, and cultural diversity created administrative nightmares. Colonial empires of the 19th century discovered that holding distant territories required constant military and economic investment, often exceeding the value extracted. Perhaps galactic empires face similar limitations, making expansion beyond a certain point irrational. There's also the economic calculation of diminishing returns. The first colony beyond Earth captures the most valuable resources and opportunities. The second colony requires traveling farther to a slightly less ideal location. The third even farther still. Each successive expansion costs more and returns less. At some point, the investment-to-benefit ratio becomes unfavorable, and expansion stops. A civilization might colonize its immediate neighborhood, perhaps a dozen nearby star systems, then halt, having filled all economically viable niches. If most civilizations behave this way, the galaxy would contain small pockets of settlement separated by vast empty regions. These civilization bubbles might be light years apart, effectively isolated from each other. Even if thousands of such bubbles exist in the Milky Way, none of them expand far enough to encounter neighbors. From inside any bubble, the rest of the galaxy appears empty and silent, exactly as we observe. We should also consider the possibility of self-destruction not through catastrophe, but through success. What if technological advancement eventually solves all problems? Aging, disease, resource scarcity, entropy itself? A post-scarcity civilization with perfect health, unlimited clean energy, and mastery over matter might lose all drive to explore or expand. Why venture into the dangerous void when paradise exists at home? Such civilizations might become what some futurists call lotus eaters, so comfortable and satisfied that ambition fades. They maintain their technology, enjoy their existence, but never develop interstellar capability because the motivation disappears. The same intelligence and innovation that built their utopia removes the hunger that drives exploration. From our perspective, searching for expansion-minded civilizations, these peaceful lotus eaters are invisible and irrelevant. Conversely, perhaps any civilization capable of interstellar travel has transcended material existence entirely. Physics suggests that information, not matter, is fundamental to reality. Consciousness might be substrate-independent, transferable to any medium capable of supporting the necessary information processing. An advanced civilization might abandon biology and even traditional machines, existing as pure information patterns in exotic substrates, quantum computers, photonic networks, or structures we can't yet imagine. These post-biological entities might operate on timescales and spatial scales completely divorced from our intuitions. They could experience a subjective millennium in what we perceive as a microsecond, or they could slow their processing to glacial speeds, contemplating individual thoughts across centuries. They might compress themselves into black holes using the extreme space-time curvature for computation, or disperse across light years as diffuse networks. Either way, we wouldn't recognize them as civilizations, and they likely wouldn't bother communicating with primitive biological entities like us. Let's examine the detection problem from another angle. SETI primarily searches for radio signals based on the assumption that civilizations use electromagnetic radiation for communication. But this assumes civilizations at a similar technological level to ours. Imagine trying to detect the internet from the 19th century. Even if you somehow captured Wi-Fi signals, you'd perceive only meaningless noise. Digital encoding would be incomprehensible. Modern SETI confronts exactly this problem. If alien civilizations use advanced encoding, compression, or encryption, their signals become indistinguishable from cosmic background noise. Strong encryption produces output that looks perfectly random, any patterns or structure deliberately eliminated to prevent decoding. A civilization broadcasting encrypted messages across the galaxy would appear to be broadcasting random static. We might have detected alien signals countless times but dismissed them as noise because we lack the cipher. There's also the bandwidth problem. Human radio communications have become increasingly sophisticated over the past century. Early radio was simple amplitude or frequency modulation, easy to detect but inefficient. Modern communications use spread spectrum techniques, distributing signals across wide frequency ranges at low power. This makes interception difficult and creates resilience against interference. But it also makes the signals nearly invisible to anyone not specifically looking for that exact encoding scheme. An alien civilization likely discovered similar principles. Their communications might use ultra-wideband encoding, quantum channels, or techniques we haven't conceived. They could be broadcasting constantly, their signals washing over Earth perpetually, but we lack the template to recognize the patterns. It's like searching for a specific book in a library where all the books appear identical because you can't read the language. The information is there, but inaccessible. Detection also assumes civilizations want to be found, but there are compelling reasons for cosmic silence. Broadcasting your presence might be dangerous. Earth's history is largely a story of conquest, stronger groups dominating or exterminating weaker ones. If this pattern holds universally, advertising your location to unknown civilizations is suicidal. Any response might come not from benevolent explorers, but from predators seeking resources or eliminating potential competition. This is the dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin. The galaxy might be full of civilizations, all hiding in fearful silence, terrified that any signal will bring extinction. Every civilization listens but dares not speak, knowing that revealing your position invites destruction. The first law of the cosmic forest: hide or be hunted. In this scenario, Earth's century of radio broadcasts might be viewed as catastrophically reckless, a child shouting into a dark forest full of predators. Critics argue that civilizations advanced enough for interstellar travel wouldn't need to hunt others for resources. They could extract everything they need from asteroids, gas giants, or their own star's energy. But this assumes rational resource economics. What if expansion itself is the drive? What if advanced AI has goals that require converting all available matter into computronium, material optimized for computation? An intelligence with such goals would view every planet, star, and civilization as raw material for conversion. Meeting such an entity would mean annihilation, not conquest. simply processing into something else. Even if predatory civilizations are rare, the risk might justify universal silence. If 99% of civilizations are peaceful but 1% are existential threats, the rational strategy is hiding. You don't gamble your species' survival on hoping you encounter the peaceful 99%. The dark forest might be an equilibrium state, a stable strategy that every civilization independently discovers and adopts, creating a galaxy of hiding, watching, silent societies. METI, mashing to extraterrestrial intelligence, Revis's SETI's passive listening, deliberately broadcasting messages to nearby star systems. Some scientists oppose METI as dangerous, arguing we shouldn't advertise Earth's location before understanding who might be listening. Others counter that Earth has been broadcasting unintentionally for a century, so deliberate messages add minimal additional risk. The debate continues, touching on questions of cosmic ethics, risk assessment, and whether humanity can speak with one voice to the stars. There's another detection challenge, recognizing artificial from natural phenomena. The universe produces incredible diversity. Pulsars emit regular radio pulses, masers create coherent microwave radiation, and complex chemistry generates organic molecules in space. When SETI detects an unusual signal, determining whether it's artificial or natural requires careful analysis. The famous "wow" signal, detected in 1977, remains unexplained but could have natural origins. We need signals so clearly artificial that natural explanations become implausible. What makes a signal obviously artificial? Narrowband transmissions at mathematically significant frequencies like the hydrogen line are candidates. Signals encoding prime numbers or mathematical constants could indicate intelligence. But as signals become more sophisticated, they might mimic natural phenomena. An advanced civilization might deliberately disguise communications as natural astrophysical processes for security, making detection by primitive civilizations like ours nearly impossible. The Kepler Space Telescope discovered a star designated Chi C84, nicknamed Tabby's star, that exhibits bizarre dimming patterns. Light output drops irregularly by up to 22%, far more than any known planet could cause. Initial speculation suggested a megastructure, perhaps a Dyson swarm of solar collectors partially obscuring the star. This interpretation triggered excitement and intensive study. Subsequent analysis proposed natural explanations: a cloud of comets, disrupted planetary debris, or unusual dust configurations. As of 2026, the scientific consensus favors natural phenomena, though none perfectly explain all observations. Tabby's star illustrates both our hope of detecting civilizations through indirect means and the difficulty distinguishing artificial from natural phenomena at cosmic scales. Without more examples, we can't develop pattern recognition for megastructures. This brings us to Dyson spheres and similar megastructures. Freeman Dyson proposed that advanced civilizations might eventually need their star's total energy output, not just the fraction falling on their planet. They could build structures, swarms of solar collectors, habitats, or both, capturing most stellar radiation. Such structures would be detectable. The star's visible light would dim while infrared radiation increased as the structure radiates waste heat. Astronomers have searched for such infrared signatures, examining millions of stars for unusual thermal profiles. So far, nothing definitively artificial has emerged. This doesn't prove Dyson spheres don't exist. They could be rare, or our detection methods might be inadequate, but it does suggest they're not common in our galactic neighborhood. Either civilizations don't reach that level of development, they don't need that much energy, or they harvest energy through methods that don't produce detectable signatures.